Hmm. Come on in, everyone. Anybody have any questions before we get started? All right, doesn't look like anybody has any questions, so I guess it's about time we should probably go ahead and get started. So we're in chapter 23, which is on electric potential, which we also call voltage, which is not the same thing as electric potential energy. If the word energy is ever in there, remember we're talking about potential energy, which we use the symbol U for, and has units of joules. Whereas if we're talking about the electric potential or the voltage, we're talking about something that's measured in joules per Coulomb, which is the volt. Okay. So just keep that in mind. That'll help you stay straight with a lot of the different problems you run into. Also, remember everything we learned about conservation of energy, mechanical energy, this sort of stuff still applies. So, for instance, if something has a high potential energy, it will naturally move, meaning naturally or spontaneously, like we learned in thermodynamics, meaning it'll move on its own to a place where the potential energy is lower. So that's just something that everything does. So for instance, we saw before that electrons, or let's start off with the protons because they're the simplest. Protons, of course, if you had a proton between two plates, like a parallel plate capacitor, and one of the plates was positive, the other one was negative, and you had the proton right next to the positive plate, it would in fact have a high potential energy, and in fact, the high positive plate would have a high voltage. So the potential, or excuse me, the proton would want to move from that location next to the positive plate to the location next to the negative plate, and to do so on its own. That would both decrease the voltage because it'd go from the high voltage side, the positive side, to the low voltage side, the negative side. But it would also decrease the potential energy because it goes from high potential energy to low potential energy. The electron, on the other hand, if you put it near the negative side of the parallel plate capacitor, then the electron has a high potential energy and it doesn't like being there, but it has a low voltage. So if you allow that to just do whatever it wants to do, that electron will actually move from the negative plate to the positive plate, in which case it literally goes from low voltage to high voltage, and that's perfectly normal. Okay, that's exactly what we expect is negative charges going from the negative or the black side of a power source to the positive or the red side of the power source. However, when you do potential energy, the potential energy would actually decrease in going from the negative side to the positive side. So just keep that idea fresh in your mind, and sometimes it'll keep you from making little careless mistakes. We then know, of course, that work is equal to the change in potential energy if you're actually calculating the work being done. So if the potential energy actually decreases, then the change in potential energy would be negative, and that would mean a negative amount of work done, and that's consistent with it moving on its own. Okay. All right, so let's go on. What I want to do now is work another problem or a couple more problems. And specifically, I want to work some problems that we hadn't done in the last class. So I'm double checking just to make sure I didn't do this in the last class. I was pretty confident I didn't. Yes, I did not do it. So the last problem we did was the one where we had a parallel plate capacitor separated by a positive side that was at positive 50 volts and a negative side that was, say, at 0 volts. And we used that to calculate the electric field. We said the voltage difference from one side to the other was 50 volts, and the distance was 0.050 meters. And that allowed us to compute that the electric field strength was 1,000 volts per meter. And that gave us also a new unit for the electric field. Instead of just saying newtons per coulomb, which is a fine unit, we can now also say it's volts per meter. And I think that's a little more physical and a little more helpful. So what we're going to do now is we're going to actually calculate the actual voltage change as a result, for instance, of a positive charge, actually. Yeah, I think that's where I want to go. I'm trying to look for the actual example I want it to work. That's not the one. That's not the one. Oh, okay, here it is. Oh, darn, we got still more people coming in. Woo, a lot of people. All right, so it looks like we're now up to 13 people in the class, so that's pretty good. Now might be a good time for you guys to go ahead and chat me your first and last name, so I'll know uh, that you're here for attendance reasons. So please go ahead and do that. I don't care, like I said, if you end up leaving early, because I don't count roll in terms of points off or anything like that. But of course, it does harm you if you're not here. So I think that fixes itself. So let's begin with considering a actual charge conducting sphere. So what I want to do is determine the potential, and notice I just said potential. So I would like to determine the potential at any distance r from the center of a charge conducting sphere of radius r. So I will say it like this, and I'm going to go ahead and share my screen. Anybody have any questions before I get started? I've given you lots of times, obviously, but just in case. All right, I'm going to go ahead and share my screen then. Sneezing's fun. I'm really liking that. Every time I do it, hurts my shoulder. That's not good. Okay. So what I want to do is determine what is the potential. Notice I didn't even have to say the word electric at any distance r from the center of a charged conducting sphere of radius r and charge q. So that's the question, and that's the one we're attempting to solve. So everybody sort of understands what that is. I'll go ahead and draw it. I'll draw it with a coordinate system like so. And maybe this will be my x-axis, this will be my y-axis, and this will be my z-axis. And what I'm going to do is say this is my conducting sphere. Okay, it has a radius of r and a charge of q. And what we'd like to know is the basically the electric potential at any point. So what we can use here is we know, for instance, let's go ahead and write solution. We know, for instance, that the electric field caused by such a charged conductor is actually going to be equal to E times Q over 4 pi epsilon naught R. And we know that for R greater than big R. It's a little bit uncertain exactly without us working it out. It's a little bit uncertain exactly what the electric field would be for R less than R. And we also can say that since we're assuming the charge is Q and the Q is positive, even if it's not positive, we're going to plug in a negative number in that Q and then it would reverse the electric field. So right now, with the Q listed in it, we can actually say that the electric field will actually point in a direction radially outward. In other words, if you imagine any point in space, any point outside of the conducting sphere in space, and you imagine a line from that point all the way back to the origin, the electric field will point parallel to that wire, but away from the origin. That's the very definition of the r hat direction. And then the fact that it's an r hat vector means that it's just 1 unit long so that you can multiply it by this magnitude and still get the right vector. So I can put a vector symbol on top of it and just put r hat here and recognize that that r hat is the as described a second ago, but it's also the r hat from spherical coordinates. Okay. One thing we do know, and we've done this already, we know that delta V, which is V final minus V initial, is equal to the negative integral of E dot dl from RA to RB. And I'm putting all that on here. Remember, it's a path or line integral. And the way that works is when you actually go to complete the integral, you have to either choose the direction you're going by indicating it with the dl vector, in which case the range of integration will point in the positive coordinate direction, or you have to use the range of integration to indicate the direction, and then dl would point in a positive coordinate direction. If you do both, it can actually cause problems. In a lot of cases, and probably in most cases, it doesn't cause any problem at all. But of course, the one time you try to do it on the test will be the time that you won't get the right answer, and therefore I'm trying to teach it to you properly. Okay, so we've already done that, in fact, and when we did it, what we got was I can just go ahead and plug this in and say the negative integral from RA to RB of Q over 4 pi epsilon naught R squared, then R hat dotted with dr r hat. Notice I put the dr pointing in the positive coordinate direction, the dl, and then RA and RB would actually go from the first spot, RA, to the second spot. So the range of integration is actually dictating which direction we're going. We can actually now pull out all the constants, and I'll get a negative Q over 4 pi epsilon naught. And then I'm going to get the integral from RA to RB of dr over r squared times r hat dotted with r hat, which of course is just 1. And then, of course, you've got the integral of r to the negative 2 dr. That integral is r to the negative 1 divided by negative 1. So I can go ahead and change the sign to plus q over 4 pi epsilon naught. And now I'm going to just do 1 over RB minus 1 over RA. And that gives me really the change in voltage for any two positions. So if I go from a distance RA to a distance RB, this will actually give me the correct change in voltage for that period. Okay. So now that we have that, we can make use of it. And you're always allowed, since just like potential energy, the electric potential is somewhat arbitrary, meaning remember how when we did, for instance, roller coasters and stuff like that with potential energy, we were allowed to call the ground the zero of potential energy, or we could have called the lowest point on the actual track, we'd call that the zero of potential energy. All of that's completely fine, because in the end of the day, these electric potential, just like the potential energy, uh, usually only matters in that their change is what's important. In other words, how much did the electric potential energy change, or how much did the potential energy change, or in this case, how much did the electric potential change? That's really what's more relevant. So you can arbitrarily add any constant to it. Because of that, that allows us to set the voltage equal to zero at anywhere. So what we're going to do is we're going to first imagine for R greater than R. So let's say R greater than R. We're going to say RA goes to infinity as VA goes to zero. And I'll put that slash on there so nobody mistakes it for something other than a zero. So we can actually do that. We can set the voltage at infinitely far away to be zero, and then what's left is the voltage at B. So if I want to know what the voltage at any other spot is, I can say delta V is equal to VB minus VA. But what I've done is I set VA equal to zero. And of course, this is all equal to Q over 4 pi epsilon naught times 1 over RB. Or you can just say delta V at R is just equal to Q over 4 pi epsilon naught R. Okay? So that is really it. Notice it falls like 1 over R, not like 1 over R squared. Okay, so that's a big difference between the voltage and the electric field. This is also sometimes called Coulomb's law for the electric potential, because you can see it came straight from Coulomb's law. So that's another thing we can call it. And of course, that will be used on occasion, so make sure you're cool with that. So everybody sees now for R greater than big R, we get this. So I'm going to put the answer down, and I'm going to put a red box around it, and that shows us what we're going to get. Now I'm going to consider the case of R equal to R. So let's go back and say R equals R. In that case, delta V at R equal to R is actually just going to be Q over 4 pi epsilon naught times big R, and that's for R equal to big R. Okay, so that's another expression, though I didn't ask for us to break it down this way. I just wanted to make sure everybody was on the same page. So what we're considering by calling it delta V is, again, we're comparing it relative to infinitely far away. Now, here's the problem. For a conductor, in electrostatics, E equals zero inside the conductor. Remember, that's one of the things we use, and one of the things I've been teaching you since we got into this, but it's also what we can use with Gauss's law to show that for a conductor, when you put charge on it, all the charge will go out to the outside edge and only be there. So with this in mind, we can now say delta V at R less than R is equal to V at R less than R minus V at R. Okay, so we can say that. And then what we'll see is that basically what's going to happen is the change from an electric field, or excuse me, the change in the voltage from R equal to R to any distance inside is going to change by zero. And the reason for that is the electric field is zero. So we're going to say this is equal to the negative integral of 0 dot dl. So it equals 0. And that means that oops, that means that V at R less than R is just equal to V at R. Well, you could say V at R plus 0, so you'd see how it came from that equation right there. But that's the main thing that you see. So now what we're going to say is V at R less than big R is in fact going to be Q over 4 pi epsilon naught R for R less than big R. And that's what our answer is. Anybody have any questions on that? So unlike the electric field, when we actually make a plot of the voltage as a function of distance, R, for instance, we'll have an R here. But before, what we had for the electric field was the electric field, for instance, had 0 everywhere inside the conductor. And so I'll draw that in blue, for instance. So we'll say this right here is this, and I'm going to say this is the electric field. And then what we found out is right about here, okay, that's where the electric field stopped being 0, and then it fell off rather rapidly like this. Proportional, in fact, to 1 over r squared. Now, and actually I should probably write this in purple instead of red, so let me do that real quick. So the electric potential, on the other hand, we will see is in fact, and I should go ahead and put this value right here. I'm going to say this value in blue is, of course, Q over 4 pi epsilon naught r squared. But in purple, this value is Q over 4 pi epsilon naught r. Okay. So now this one becomes like this, and then it falls off like 1 over r. Okay, so you can see in one graph how different the electric field magnitude is versus the voltage magnitude, and so on and so forth. Anybody have any questions on that one? All right, so there's another problem, and what we're wanting to do is basically show that the breakdown voltage is directly proportional to the electric field strength. So it turns out that when you subject our atmosphere, which is generally considered a insulator, a non-conductor, when you subject it to strong enough electric fields, then what can happen is the electric field strength can be so high it can strip electrons. Well, in principle, if it's really high, you could strip electrons straight from the atoms, or you could just accelerate the few free electrons that are around from gamma rays and whatnot that have hit in the upper atmosphere. You can cause those electric field, or excuse me, those electric particles, which would basically be electrons. You can cause those electrons to move rather rapidly, and then those electrons can collide with nitrogen and oxygen, which is the lion's share of the elements in the atmosphere. And when it does, it actually can dislodge electrons and actually create yet another path. So you end up getting a series of weird shaped lines, basically from free charges to the next free charge to the next free charge. And that's exactly what happens when lightning strikes. Once you get a high enough electric field strength between two spots, maybe a cloud and the earth, what happens is the electrons are compelled to basically build a charge locally in various spots, and then the electricity will fire off either from the cloud or from the ground, and then follow that path. And that's why the patterns are so jiggly back and forth, and so on and so forth. So what we want to do is show that the breakdown voltage, and by the way, the breakdown for the air, so the electric field required to ionize air is about E breakdown is equal to 3 times 10 to the 6 volts per meter. Notice that's our new unit of the electric field. Okay. And what that's saying is if you actually have a voltage of 3 million volts between two objects that are 1 meter apart, then lightning will strike and bridge that gap of 1 meter. Obviously, if it's 100 meters, you'd have to have 300 million volts, and so on and so forth. But that's what we're going to use now. And what we want to do is show that, whoa, Nelly. I want to show that the breakdown voltage, ah, dang it, which is given the symbol VBD, is breakdown voltage VBD, ah, dang it, for a spherical conductor is proportional to the radius of the sphere. So that's one part that I want to do. And then the other part, which let's call this one A, and we'll call this one B. And the other part I would like to estimate the breakdown voltage for a sphere of diameter D equal 1.0 millimeters. Okay, so that's our goal here. So what I do know is that the voltage for a conducting sphere is equal to Q over 4 pi epsilon naught times, let's say, R, the radius of the sphere. We also know, of course, that the electric field for that sphere is Q over 4 pi epsilon naught times R for that sphere, excuse me, times R squared for that sphere. That's what our electric field strength is. So from that, I think you can automatically see that V breakdown would actually equal to just plain R times E breakdown because you can see that if you multiply R times E, you get V. That's going to cause this to that. And then now you get V. So that's exactly why it is. And this is at the surface of the sphere. Okay, so that's what we were shooting for. And we've done that. So we can even put a QED here if we want to. And we're now done with part A. Now, part B wants us to actually decide or estimate roughly what that breakdown voltage is for a sphere whose diameter is 1 millimeter. So that's a really small amount. So let's do part B. Part B, V breakdown would actually equal 0.00. Remember, a millimeter would be the third decimal place, so I'd have a 1 there, but that's the diameter. I actually want the radius, so I got to put another 0 and then a 5, and this is meters. So that's my R, and then times the breakdown voltage of the air, which is, dang it, the breakdown electric field, I should say, of the air is 3 times 10 to the 6 volts per meter. So you can see that the 5 is actually 5 over 10,000. And if I divide 10 to the 6 by 10,000, that's basically 10 to the 4th, under 10 to the 6, that'd be 10 to the 2. So this would be 5 times 10 to the 2. Actually, excuse me, 15 times 10 to the 2, because 3 times 5 is 15. So that's 15 times 10 to the 2, or 1,500 volts. Okay. The main thing that you're supposed to see from this demonstration is that if I were to make the radius even smaller, the voltage difference would be even smaller. Note, as R gets smaller, so too does V breakdown, which implies lightning. Ain't that a cool looking little lightning? Okay. So that's the main point of that whole thing. And this is the reason that lightning rods work. Lightning rods ostensibly were invented by Ben Franklin, one of the many things he did actually in science, despite having little or no mathematical education. But still, he did come up with the idea of lightning rods, and they work very well. In fact, you can actually see them if you're on our campus, and at least the Virginia Beach campus, are the new buildings at Chesapeake and new buildings in Portsmouth. Those particular locations, you'll notice they have little lightning rods everywhere. Those lightning rods can sort of be thought of as if they're little cylinders with a little sphere on the end, and it turns out that the smaller that radius of that sphere is, the smaller the voltage difference between it and some cloud, for instance, has to be in order for lightning to discharge from the cloud to the actual lightning rod. And in fact, you'll even get a little, what we call a coronal discharge, a glow around the tips of the individual lightning rods. That's called St. Elmo's fire. For people that are old like me, we know of a movie called St. Elmo's Fire. And in fact, today I learned that the word for that in Latin is castor, Castor. So that's kind of a neat little thing. But anyways, yeah, St. Elmo's Fire, like the movie with Judd Nelson and all those other people that made us laugh, and Pretty in Pink and 16 Candles and all that good stuff. All right, so that's enough for that one. Anybody have any questions on this? Okay, so that little calculation we did right there with the previous example where I had delta V is equal to VB minus VA is equal to the negative integral of E dot dl. Without that negative integral E dot dl, in other words, once we actually did that integral, we got Q over 4 pi epsilon naught times 1 over RB minus 1 over RA. That can be used over and over again because the electric potential is just a scalar, and that's the way we work with it. So if you want to think about how much work is being done from one thing to the other, that's the place we can start. We just know that delta V is going to be VB minus VA, which is Q over 4 pi epsilon naught times parenthesis 1 over RB minus 1 over RA. So let's think about this one. I think I can fit this in this problem. So let me change colors real quick so I can put a line between this problem and the next. There you go. There's a line. And let's say this time we're going to see, whoa, Nelly. I'm writing with the automatic edit thing. So what is the minimum work? Ah, dang it. Done by an external force to bring a charge a Q equals 5.00 nanocoulomb charge from a huge distance away to oh, to a point 0.050 meters from a charge Q is equal to 50.0 nanocoulombs. Okay, so that's a question we can answer. What I want you to think though is, hey, for instance, we found earlier that the change in voltage in one particular scenario was the electric field times the distance. Does anybody recall in what scenario that was the actual change in voltage, namely the constant electric field times D? Because the reason I bring this up, it's not necessarily a good thing to bring such a thing up, but I want to, I know this is something that students keep doing, and I don't know why, but it's literally only like 4 out of 20 students do it just about every semester. They think that V equals ED is like some applicable equation for just about everything, and it's not, okay? That was derived by calculating the integral, which is the negative integral of E dot dl for a constant electric field. So when we're talking about bringing a 5 nanocoulomb charge in from a huge distance away, which we'll all read as infinity, what we see is that this charge Q, 50 nanocoulombs, is creating an actual electric field, and that electric field is not uniform. It's going to change. So in general, what you'd have to do is integrate that. But the good news is we don't have to do that because we know that we can find the work because work is equal to the change in potential energy. So what we're going to do here is we're going to say solution work is going to be equal to, dang it. is going to be equal to the change in potential energy. And of course, the change in potential energy is going to be just Q times the change in voltage. Okay. So we can avoid all that integration stuff just by using the work and energy process like we learned in 241. So what we know here is that Q is going to be our 5.00 nanocoulombs. So I'm going to write 5.00 times 10 to the negative ninth coulombs times, now my delta V is going to be, in fact, 50.0 times 10 to the negative 9 coulombs divided by 4 pi epsilon naught. Remember, this is the final position, so this is the position that's 0.050 meters away. So 4 pi epsilon naught times 0.050 meters, like this, and then minus, in this case, we're taking the limit as r approaches infinity of q over 4 pi epsilon naught r, like that. So we can see that in doing that, obviously this type becomes, or this term becomes 0. So when I do this, I'm ultimately going to get 5 times 10 to the negative ninth times 50 times 10 to the negative ninth, 5e negative 9 times 50e negative 9 divided by parentheses 4 times pi times 8.85 e to the negative 12. That's Coulomb squared per Newton meter squared. So that Coulomb squared per Newton meter squared, the Coulomb squared is going to cancel out with the 2 coulombs. The Newton meter squared is in the bottom of the denominator. So one of the meters is going to cancel out, and we're going to have a Newton times a meter, which is basically a joule in the bottom of the bottom, which means a joule will come up on top, and then we'll have a joule per coulomb, which is a volt. But that volt multiplied by the actual coulomb on the other side will actually give us the joule. So 8.85 times 10 to the negative 12th times 0.05. Hopefully you guys are doing these calculations as well. So if I make a mistake, you'll catch me. So I got 5 times 10 to the negative ninth times 50 times 10 to the negative ninth divided by parentheses 4 times pi times 8.85 times 10 to the negative 12th times 0.05. And this gives me 4.50 times 10 to the negative fifth joules. And that looks pretty good to me. Yep, that's it. Any questions on that? All right. So that's actually a very small energy, but of course it's a lot easier than doing the integral and all that good stuff. So this is just an easy way to calculate it. Hopefully that'll help you. You'll see that your book has an example very much like it. I'll say this is like example 23-6. So if you don't necessarily understand what I was saying or anything like that, you can always turn to that example. And of course, that's going to be in your notes anyways, which you have access to not only through the video, but you also have access to it through my Google Docs. So anybody have any questions on that? All right, your book does a really nice conceptual example. I say it's somewhat conceptual. Oh, actually, hold on. Oh, no, this is a different problem. So yeah, I want to do one involving a actual electric dipole. So let's go ahead and draw a coordinate system. I'm going to draw a coordinate system like this. like that. Okay. And what I'm going to do is I'm going to say there's a charge right here that's going to be Q up. I'm in the auto change stuff. I want to say Q is equal to positive, let's say 80 microcoulombs, and I'll assume that's 2 sig figs, so I'll put a little dot there after it. And I'm going to say this distance right here is 26 centimeters. Then I'm going to say over here is another 26 centimeters. And right here is a Q equal to negative 80 microcoulombs. And then I'm going to go up here and say that this distance right here is 30 centimeters, like that. And what I'd like to do is calculate V there. And I'd also like to calculate, let's call this V at A, and let's call this V at B. Okay, so I want to calculate the electric potential at those two locations. Okay. So that's what our problem is. Our problems are, I should say. And I'm going to say solution. Now here's the cool part. This is so much worth what we're doing. Now that we're working with actual voltage as opposed to electric field and the force, then we don't have vector quantities, so that makes it really easy. You can also check and see that if you take 30 squared plus 26 squared, I'm going to do 30 squared plus 26 squared. That gives me 1,576. When I take the square root of that, you can see that it comes up to right at 40 centimeters. So that tells us this distance right here is essentially 40 decimal centimeters. Additionally, if you take 52 squared plus 30 squared, you get 3,604, which is really, really close to 60 squared. In fact, if you raise that to the 0.5 power, you get 60.03. So what I'm going to do is say that this distance right here is really about 60.0. In other words, if we rounded it to one decimal place, it would still be 60.0. Just like if we rounded the 40 to one decimal place, it would still be the 40. So that helps us a little bit by knowing those distances already. So let's begin. The V sub A is equal to the V at A due to the positive charge plus the V at A due to the negative charge. And of course, the V at A due to the positive charge is in fact 80 times 10 to the negative 6 coulombs over 4 pi times 8.85. I'm going to leave off the units here because we've done enough seeing them, times 10 to the negative 12. And then, of course, that distance is 0.40. So I left off that unit. And now I've got to add to that the one due to the negative charge. And you can see, of course, by symmetry that that also is 40 centimeters. So I'm going to say in this case, it's going to be negative 80 times 10 to the negative 6 coulombs. Again, leaving off the rest of the units. 4 pi times 8.85 times 10 to the negative 12 times 0.40 meters again, but again, I left off the units. So you can see no matter what, the top number and the bottom number in this addition are equal to each other, but opposite in sign. So the voltage VA is equal to 0. So our first answer is V at A is equal to 0 volts. Any questions on that one? Now I'm going to do VB. At this time, though, I'll make sure VB has a lot more room to be written out. So now let's go to VB. So the voltage at B is equal to the voltage at B due to the positive 1 plus the voltage at B due to the negative 1, which is obviously going to be 80 point, well, actually I shouldn't include a 0.0, but I'll put 80 times 10 to the negative 6 coulombs. I'll go ahead and show all the units on this one. That's due to the positive 1, so we got 4 times pi times 8.85 times 10 to the negative 12th coulomb squared per Newton meters squared, which you can go ahead if you wanted to and rewrite those units in terms of volts. That comes in kind of handy, but we don't have to. So now I'm going to take this and multiply it times the distance, which from the point B, the distance is actually 0.60 meters. And then I'm going to add to it the one from the negative, and this time it's going to be negative 80 times 10 to the negative 6 coulombs divided by 4 times pi times 8.85 times 10 to the negative 12th. Again, coulomb squared per Newton meter squared. But this time, this one's only 30 centimeters away because it's directly above it vertically. So it's going to be 0.30 meters. So I think you can tell by looking at these units, I've got a coulomb that's canceling out with one of the coulombs down below. The Newton meter squared will come on top, and one of those meters will cancel out. So I have a Newton meter on top and a Coulomb on the bottom, but a Newton meter is a joule, and a joule per Coulomb is a volt. So we see that we do in fact get volts for this. So I'm going to say 80 e to the negative 6 divided by parenthesis 4 times 3.14159 times 8.85 e to the negative 12 times 0.6 close parentheses. That's just the first term. And that gives me 1.199 times 10 to the 1, 2, 3, 4, 5, 6 times 10 to the 6 volts. Obviously, I only had 2 sig figs, so those 2 nines are extra sig figs. Now I've got the other number, which is going to be plus a negative, so I'll just write it as minus. In this case, I'm going to say 80 e to the negative 6 divided by parentheses 4 times 3.14159 times 8.85 e to the negative 12. Oh, this is looking pretty good so far. Times 0.3. And then close parentheses. In this case, I get 2.398. Obviously, the 9 and the 8 are not sig figs. And that's times 10 to the 6 as well. And again, I did say that that was equal to volts. So I can do this should give me, in fact, a negative quantity, and it's negative 1.2 times 10 to the 6 volts. Any questions on that? Anybody have any corrections? Hopefully you all were calculating this the same time I did and, you know, can check my work for me and all that good stuff. All right. Well, your book does do a good little conceptual problem. That's what I was getting ready to talk about a second ago, but then I remembered I needed to do this problem. So let me put a line here just to bar this from the rest. Okay, so now we're going to look at this conceptual problem. Your book wants wants us to figure out something. So what I'm going to do is I'm going to say, here's a charge, and here's a charge. Well, and then two similar charges again, but a little further apart. Okay, and then about the same distance apart. I would like to just cut and paste that, but it looks like I can't, or I could, but it just take too much trouble. So I'm going to try to do the same thing here. Obviously, I made it entirely different size, but the main thing is we're all pretending these are all equal amounts of charges. So what I'm going to do is I'm going to say uh, this guy is positive, this guy is positive, this guy is positive, this guy is also positive. However, let's say this one's negative and this one's negative. So this charge will in fact be negative Q, positive Q, positive Q, positive Q, and positive Q. And what we'd like to know is which one has the highest potential energy and which one has the most negative potential energy. Okay. So what we know is that the potential energy is really the work done. So we could say work done by the external force is equal to the change in potential energy. But that change in potential energy, in fact, is equal to basically one of the charges, let's say Q times the voltage created by the other charge, and the voltage created by the other charge is Q over 4 pi epsilon naught times R, where R is the separation. Okay. So in fact, we could subscript these just to make it a little more concrete. So I could say this one's Q1, and I could say this one, for instance, is Q2 or something. But that's the main thing is your formula ultimately is going to be U is equal to Q1, Q2 over 4 pi epsilon naught times R. So we see by looking at this that this one has two positive charges. So U is going to be greater than 0 because it's positive times a positive, right? And that's in fact going to be the only one that will have a positive potential energy. So the potential energy is positive, and this also implies this is the greatest potential energy of the three. Okay. And that we should expect, right? Two positive charges next to each other. They don't like that. right? They don't want to be there. In fact, if you let them go, the two charges are going to run in opposite directions to try to get away from each other. Now, in the next scenario, we have U is actually negative. So for this guy, we have U is less than 0, but R, which I'll call R2, but R2 is greater than R1. So U is less negative. Okay. And then this one right here, U is less than 0 and has high potential energy magnitude. I could say highest. In fact, let me go ahead and get rid of this and just say, so that one's the highest potential energy. And that should make sense. So that top one, if you let it go, they're going to immediately slam into each other. But in fact, they would take the largest amount of work to separate them. The middle one would take less work to separate them, but still more work than the, or still, yeah, more work than the bottom ones, because the bottom ones wouldn't take any work at all. They'd take a negative amount of work. And that negative amount of work means they're just move apart. So hopefully that helps you. This again is like example 23.8. So I'll say. Does anybody have any questions on that? All right. So that I think is enough to really solidify the concepts with uh, voltage in general. What we need to move on to now is I've already covered the electron volt. I will tell you that this book has a ton of really interesting and useful stuff that I'm not requiring you guys to know at all. So for instance, starting at section 23.9, it talks about digital binary numbers, signal voltage, noise and digital transmission, TV and computer monitors, CRT, digital TV and addressing pixels, active matrix, oscilloscopes, electrocardiograms, all that stuff. All of those things are going to be completely optional. If you have any intent of going into either computer programming or electrical engineering or computer engineering, then I'd say it's probably very, very wise for you to read that and take notes and make as much sense of it as you can. But I'm not going to require any of that. So nothing after section 23.8 is relevant for our class. But what I still have to do is one, I have to talk about building up charge distributions. So for instance, if you think about trying to build up a distribution of charges, you can say, okay, I'm going to bring a charge Q1 in. Well, if you're dealing with that being the very first charge, then you sort of imagine that there's no other charges anywhere around. So that one's a freebie. You just bring in Q1 and you plop it down. That's now established a voltage of Q1 over 4 pi epsilon naught R, where R is the distance you are away from Q1. Then if you bring another charge Q2 down to it, then there's going to be some work done in bringing it however close to Q1 that you want. That work we just discovered was Q1, Q2 over 4 pi epsilon naught R12, where R12 is the distance between them. Now, if we bring down another charge Q3, then we've gonna do some work that'll be equal to Q3 times Q1 over 4 pi epsilon naught R31. but also Q3 times Q2 over 4 pi epsilon naught R23. Okay. As you can see, you're going to have to keep doing this every time. So if I bring in a fourth one, now the fourth one is going to get a work done by bringing it close to Q1, a different work by bringing it close to Q2, and a different work by bringing it close to Q3. You might be tempted to just do like a double summation from I equal 1 to n of the summation from j equal 1 to n. But if you do that, then you're going to have a term that's like Q1, Q2 over 4 pi epsilon naught R12, and then another term, Q2, Q1 over 4 pi epsilon naught R1, R2. That would be a problem because you're double counting. Not only that, you're also going to get a term like Q1, Q1 over 4 pi epsilon naught R11. That term wouldn't make any sense because you're talking about the work done and bringing a charge next to itself, and that doesn't happen. So that's the only thing. And I even put a comment in the book. So if you're looking through the online book, you'll see that I put a note on there, or at least highlighted a note they already gave you. So I just wanted to point that out to you. That's something you got to keep in mind. You don't want to count the same thing twice, and you don't want to skip anything, but you also don't want to count, an object acting on itself. That doesn't happen. So with that being said, I'm going to go right to the integral part, which is sort of the last thing from this chapter. And basically, for any number of charges, you could have that the voltage at, let's say, point A is equal to the summation from I equals 1 to n of V sub I. Okay. And what I mean by that is if we are at some location we call A, then what I'm going to do is take 1 over 4 pi epsilon naught, and I'm going to take the sum from I equals 1 to n of Q sub I, so Q1, Q2, Q3, Q4, over R sub IA. So in that case, you're doing R1A, R2A, and of course that's Q1 over R1A plus Q2 over R2A plus Q3 over R3A, so on and so forth. That's how you do with a discrete sum. Of course, if you didn't have that, you could have a continuous sum, in which case you're going to say V is equal to 1 over 4 pi epsilon naught times the integral of dq over r. And as always, dq could be lambda dl, or it could be, actually, let me take away that. It could be sigma dA, or it could be rho dV, where dA is an area element and dV is a volume element, so on and so forth. So anybody have any questions about that part? I'm getting ready to do a problem to help you understand it. So let's start off and calculate the uh, voltage at a distance z above a ring of charge. So what is the electric, it's supposed to be an R, it didn't look like an R, electric potential at a distance z above the center of a ring of charge Q, and I'll say uniformly distributed, center of a ring of charge Q, and of radius big R. Okay, so that's our problem. I will go ahead and draw a coordinate system just to help us see what we're doing here. And this coordinate system is going to look like this, and this. That's going to be my x-axis, that's going to be my y-axis, that's going to be my z-axis. And in fact, I will draw a ring of charge like so. And in fact, it is a ring. Dang it. It is a ring. So there's the extra thickness I have. And that thickness is not a very big thickness, so we don't have to worry too much about that. In other words, like if the radius is r, the thickness will be like 1/100th of r, so it's not that big a deal. And in fact, what we want to do is find the voltage at this point P, which is a distance Z above. Okay? So what we're going to do is consider just a wee bit of charge, if you will. So let's do solution. V is equal to the integral of dq over 4 pi epsilon naught r. I have to integrate that. What I'm going to do is picture a little bit of charge right here. That's going to be my dq, or actually, since I used a big Q there, I could use a big Q, but it doesn't really matter too terribly much. The main thing is that the distance between it and the point Z is R is equal to the square root of Z squared plus R squared. So now I can say V is equal to 1 over 4 pi epsilon naught times the integral of dq over, now I'm just going to take the square root Z squared plus R squared. Notice the dq has no terms in it that have anything to do with big R or Z. In fact, if I really wanted to make that dq, it'd just be big R d theta, and the big R is a constant, so we don't even have to deal with it. So this actually becomes 1 over 4 pi epsilon naught square root Z squared plus R squared times the integral of dq, which ultimately gives us V is equal to Q over 4 pi epsilon naught square root Z squared plus R squared. Easy peasy. It is a scalar quantity, so that makes it a little bit easier to begin with. And that's it. Anybody have any questions on that one? Now let's do another one. This time it's going to be a charged disk of radius r. Okay. So I'll draw my coordinate system again, but I'm also going to draw an oval, something like that. Now I'll draw my coordinate system, which looks like it should go right from here, and then from here, and then from here. I'm going to call this my x-axis, going to call this my y-axis, call this my z-axis. And in fact, this is going to be Z. That's in fact the point at which I wish to know the voltage. That's the problem I'm solving. This guy is going to have a radius big R and a total charge Q. I'll say Q is uniformly distributed. Okay, and uniformly distributed, by the way, means sigma equals a constant. So what that means is Q over pi r squared is equal to, let's see, I'm going to try to make another oval like that, okay? And this one has, in fact, a radius little r, and it has a width dr, so that that little guy is the charge dq. And what we get over here is that dq over 2 pi r dr. Okay, so when I say something's uniformly distributed, that means that it's uniformly distributed over the whole volume or the whole surface or the whole length. In this case, it was essentially a two-dimensional object, a thin disk. Therefore, the obvious choice is over the area. So I made sigma do that, and that gives me, of course, that tells me that dq is in fact equal to big Q times 2 pi r dr over pi r squared. Okay, so I can now say V is equal to 1 over 4 pi epsilon naught times the integral dq over r. So this becomes 1 over 4 pi epsilon naught. Then the integral is Q times 2 pi r dr over pi r squared, and then times the distance that is from z, which in fact will be the square root of z squared plus r squared, like that. Okay. Now, if you look, you can save you a little bit of trouble in writing a bunch of stuff by just realizing that this little quantity right here is sigma. So that makes a lot of things a little easier to deal with, so we don't have to completely write this big mess every time. So I'm going to write this as sigma, and then notice this 2 right here is going to cancel out with this and leave a 2, and this pi right here is going to cancel out right here. So I'm going to say this is sigma over 2 epsilon naught, which is useful because remember we did discover that for an infinite plane, sigma over 2 epsilon naught was the electric field strength above it. In other words, it had no dependence whatsoever on distance. Now, what I have to do this integral is I need to let u equal z squared plus r squared, then du is equal to 2r dr. So what I need to do is multiply by 1 over 2 and then multiply by 2 as well, so that that RDR becomes 2RDR, which is just du. So I'm going to put this little 1/2 out in front. We'll see that it'll disappear later, so it's not that big a deal. And now I have the integral of du over u to the 1/2 power. Okay, that's u to the negative 1/2, and of course the integral of u to the negative 1/2 is u to the positive 1/2 divided by 1/2. So that's going to cancel out the 1/2 that I have in front. So now I can say equals sigma over 2 epsilon naught. Notice the 1/2 I already told you about, it's going to disappear. And now I'm going to have, instead of u to the negative 1/2, I have u to the 1/2, which I'm going to write in curly brackets and say it is the square root of z squared plus r squared. And of course, that means I'm going to integrate it from r equals 0 to big R. So I can say V is equal to sigma over 2 epsilon naught. And then this is going to be the square root Z squared plus R squared minus, now we're going to let little r become 0, and that just becomes the square root of the square of z, which is just the absolute value of z, basically. Okay, the absolute value you don't have to pay much attention to, but that is the actual voltage right there. Okay, any questions on that one? Okay, you can go ahead and put back in the Q and all that good stuff if you want. And if you did do that, it would be V is equal to, let's say Q over 4, or over, excuse me, 2 pi epsilon naught times, yeah, times R squared times the square root of Z squared plus R squared minus the absolute value of z. Now, I'll also tell you, and you can look this up in your book, but basically, we could now, it would be smart first to factor out a z and put it out in front, but there is a way to get the electric field now out of the actual voltage. And the way we do that is this. It turns out that E is actually equal to the negative gradient of V. That's a big whole process in electricity and magnetism. And I'll remind you that the gradient is actually a vector operator. So you sort of look at it as if it has this little slot next to it where it's waiting to take something that it can act on. And then you put I hat, partial derivative with respect to x, and of course leave a little spot again, plus j hat, partial with respect to z, again, leave a little spot for it to operate on something, and then plus k hat, partial with respect to z, again, leaving a little spot. Now, it's a lot more complicated if you're using coordinates other than Cartesian coordinates, but that's basically what it is. That's called the gradient. And that's how you could get it. So you can look at the examples. We are done with chapter 23. Feel free to ask me any questions. I've already put test 4 up. That's the online tests, which covers chapters 21 and 22. They are due the day you come back from spring break, which would be, or actually it'd be due the day before you come back from spring break. So you have to have it done Monday night.
I haven't done the practice test yet. It's still open, right?
Yeah. But you have, like I said, till March 10th or the 11th, whatever the Monday.
Okay, I just want to make sure because I hadn't done that and you just put the online test up. I want to make sure I didn't close the practice test yet.
Yeah, I didn't do that. I will be posting a practice test for the face-to-face one. And remember, the face-to-face test is going to be due when you get back. Since you guys meet on Tuesday, I believe your lab is on Tuesdays, and you'd have to check. Well, not yours specifically, Shonda, but the Monday lab, which is my 241 class, they're not having their face-to-face until the week after we return. Whereas, as far as I know, Tuesday, Wednesday, Thursday, Friday, all their labs are going to, or all their uh, face-to-face exams are going to be immediately when you get back. So I will have this posted. I'll send an email to remind everybody. Remember, when you come back from spring break, there will be a comprehensive a comprehensive final exam. Why did I say final? Midterm exam, and it will at least cover
Midterm.
23. Yeah, it'll be a midterm. So it'll at least cover chapter.
Okay, and we do have a lab tomorrow, right?
Yes, you have a lab tomorrow. It's an optics.
Okay. Oh yeah.
All right, you're free to go, guys. I'll wait for the last person to leave in case anybody has any questions. See you, Shonda. It looks like only two people
Professor
left.
Younger.
Yeah, Micah, what's up?
Oh, yeah. So I missed last class, like last Thursday, and I was trying to look at the VOD on YouTube for voltage, and
Mm-hmm.
I think you accidentally duplicated that video with one of your 241 videos.
Oh, that's not good. Well,
Yeah,
let me check that real quick because I
yeah, because I
remember.
was like 7 minutes into it, and you started talking about like mechanic stuff. I was like, what the heck?
Okay. Introduction to electric potential. Yeah, that should be the right one where it says 4 days ago, introduction to electric potential.
Yeah, I'm gonna try to pull it up real quick.
No, it does say 241, so there's a good chance that you're right on that. Let me look at the notes. I'm 19 minutes in, and yeah, that's definitely the wrong one.
Yeah.
Oopsie. Okay, so you probably want the right one. I'll put the
Hmm.
right one up tonight. Sorry
Okay,
about that,
cool.
man.
Yeah, and then I can watch it over spring break and catch up or something.
Yeah, it shouldn't be a
So,
big
all
deal, but no problem. I appreciate you letting me know though.
right, thanks, Young. I'll see you tomorrow, man.
All right, see you. Bye bye.